Today we're going to be looking at the mean value theorem for integrals. Now, the easiest way to explain that, since it's for integrals, we're talking about the average y value of a function. So we're going to take a look at it graphically so we can make sense of what it means. For now, let's look at the formal definition, which says that if f of x is continuous, meaning no break in the graph, on the interval ab. Now this is very important because if you have no interval, then it's very difficult, if not impossible, to find the average y value. So we want to make sure we talk about the interval from a to b, so for example from 1 to 2 or from 3 to 7 or whatever. Then there exists a value c in a on the interval a to b such that the following is true. F of c, now I'm going to go ahead and label this right now. F of c is going to be representing our y value, okay? So I'm just going to put average y value. And the c is where the average is the x value where the average y value occurs. So f of c is equal to 1 over b minus a. Notice that if the interval is from a to b, then b minus a is the interval width, right? You would be taking your rightmost value and subtracting your leftmost. So 1 over b minus a times the integral from a to b of f of x. So basically there's two components to the average y value formula. Okay, the first component is just taking 1 and dividing by the interval length. Okay, so I'll just kind of label that here. And the second component, which is very easy to explain, is just the integral from a to b. Now you're probably thinking, how is this possible? Why is this true? That's what I'm going to show you. First of all, let's look at the verbal explanation of this average value. Again, the average value we're going to call f of c, and we're going to show why this formula works. Verbally, the mean value, or the average value of a function, is like averaging the infinitely many f of x values, or you could say y values, right? F of x is the same as y. So the infinitely many y values of a function on a given interval. So without further ado, let's take a look at what this would look like. I decided to start out with just a plain linear function. So this equation is f of x, or y equals 1. Now you can imagine that this green line right here, which is our function, has infinitely many points. I just plotted 5 of these pink points. But everyone should be able to see that the average y value of this function is just going to be 1, right? Because it's a straight line. So I wanted to start out with something simple. Now let's keep going. Okay, let's think about what the average y value of this line is. Now remember though, now this is the graph y equals x. Remember it has infinitely many points, okay? So again, I just chose 7 points here. But this one, intuitively, you can tell that since it's at a 45-degree angle, meaning it's not closer to the x or the y axis, it's in the middle, we can actually see that the average y value is going to be smack dab in the middle. Now, again, we are talking about a particular interval. We're starting at a equals 0, and we're going up to b equals 1. So we can see that pretty much, if we look at this graphically, the average y value, if we averaged all these the y value of these pink dots, it's going to be 1/2, right? Because again, it's tilted perfectly that way. So average value is equal to 1/2 here. Intuitively, that makes sense. However, what we want to get to is the average y value of any graph. So for this example, we have a quadratic function or parabola. I've plotted several points on here, and the question is, what is the average y value of these dots? I mean, it's hard to say, right? Now, I did want to bring up another concept. Average x value would be simple here. If we're going from 0 to 1, like we said before, okay, so here's our b value, and here is our a value. The average x value would be just right in between a and b. It'd be 1/2, right? But no, we're talking about the average y value of these pink dots. That's what I'm going to explain to you. So here's how it works. I've decided to put 5 points on my curve, and of course this curve can be whatever, just to happen to make it look like a quadratic. And so we're asking the question, what is the average y value? If I added up all these y values and divided by 5, right, because I've plotted 5 points, that would give me a rough approximation of what the average y value is of this green function. So simple enough, right? But the real question is, if there's infinitely many y values, how in the world can I possibly figure that out? If there's infinitely many of those, I'd be dividing by n, which would basically be infinity. Well, if you look at these points on this graph, does it remind you of anything we've done in the past? I want you to think for a second, and if not, that's okay, because I'm going to refresh your memory. What this reminds me of is Riemann sums, okay? If you're trying to find the area under the curve of this green function, you could draw a bunch of rectangles, right, using Riemann sums, and the height of these rectangles would just be these y values that we just labeled up here. So I'm going to call the height of the first rectangle y1, the height of the second rectangle y2, the third one y3, which happens to be 0, right, because the curve touches the x-axis, the height of the fourth one y4, and the height of the fifth one y5. I'm also going to label the width of each of these is change in x, and I'm just going to make them all the same. So all of these have a width of change of x. In this case, it'd be around a fifth of 1, right, which would be 0.2. Again, we're going from A to B. So here's our A, here's our B. A is 0, B is 1. Now what I want you to see is the following. If I were to take the area of all of these rectangles and add them up, it would give me an approximation of the integral from a to b of f of x, right? And what I can do then, since all of these rectangles have the change of x in common, is just pull that out and then add all the y values, and that would give me, this right here would give me the area of all of these rectangles. Again, it's approximately equal to the definite integral from a to b. So far, so good. Now, since I want to get all of these y values by themselves, because I want to try to ultimately figure out the average value of this function, okay, what I'm going to do is basically divide by the change of x to get these y values by themselves. So basically what I get then is if I add all these y values up, it's the same thing as the definite integral divided by the change of x, or just multiply it by 1 over the change of x. And again, the reason I'm doing that is because this right here, now that I get all the y values added up by themselves, is going to give me something close to the average value. Now all I'll have to do is divide by 5, which is what I'm going to do. So if I divide the left side of this approximate equation by 5, that would give me the average, approximately the average value of this graph right here. But if I do it to the left, I have to do it to the right. So I'm going to divide the right by 5. So now I have 1 over 5 times the change of x times the integral from a to b of f of x dx. So basically what I did is I just tucked that 5 in over there, since I divided the right by 5. Okay, now we're one step closer to our little proof here. As we said though, this graph has infinitely many y values. So not only does it have 5, but it has n, where n approaches infinity. So you can just imagine there being infinitely many pink dots on this graph. So the average of all of those would be all of the y values that I choose, say 100, 1,000, a million, divided by n. Okay, and of course, as it approaches infinity is where we actually get our average y value. So basically, for this step, again, I'm just going to replace 5 with n, since we are talking about infinitely many rectangles, or in this case, infinitely many y values. Okay. Now here's the kicker. Okay, here's the kicker. What is n times change in x equal to? If we go back and look at our Riemann sums, as we increase these number of rectangles, or these number of y values, okay, everybody can see this change in x, or the width of these rectangles, is going to approach 0, right? However, no matter how many rectangles we have, if we multiply all the rectangles within this interval times n, okay, we're going to approach the width of our interval, right? We can't get any bigger than that because our rectangles can only be within that range. So basically, n times change of x times change in x, as n approaches infinity, is just going to give you this interval width. Okay, and I decided to make that yellow here. So n times change of x is going to give you the width of our interval, which is b minus a. So basically, I can replace n times change of x with b minus a, provided that n approaches infinity, or the number of our y values approaches infinity, since we're talking about all the y values added up on this graph, on this interval, divided by the total number of y values, which again is infinity. So that's basically the key to this proof, is we're replacing n times change of x with b minus a. And so now I've basically proven that the average of my y values, y1 plus y2 plus y3, all the way up to y sub n divided by n, is equal to 1 over b minus a times the integral from a to b of f of x. Again, that's because I got to change the n times change in x and replaced it with the interval length, which is b minus a. So as a conclusion to this proof, the average y value, which again we called f of c, at some x equals c value, is just equal to 1 over b minus a times the integral from a to b of f of x. And it's interesting to me that the average y value hinges on this integral, since integral has to do with area. Nonetheless, this is the formula, and this is exactly why it works. So if ever you forget this formula, 1 over b minus a times the integral from a to b, always just go back to this simple illustration and understand that basically if you think of it in terms of Riemann sums, or the heights of these rectangles which correspond to these y values, then you can easily derive this formula. So that's it for this simple short proof of the average y value f of c on an interval. And again, if we go back to our formal definition, this is what it looks like. If you have any other questions about the average y value on an interval of a function, let me know.